Let us continue with the same example of car ownership. As we know, the dependent variable x is binary and qualitative in nature. X is equal to 1 if an individual owns a car and 0 if the individual does not own a car. Further, x is a function of independent variable of income or y. We can use the sigmoid function shown here to estimate this model. The probability of car ownership is a function of z, and z is a function of independent variables, which is income in this example. We can also express the sigmoid function in a way shown here. Both these expressions are inherently the same, we simply express them in a different manner using mathematical tricks. As we have expressed pi or probability of car ownership using the sigmoid function, we can also obtain the probability of not owning a car, which will simply be 1 minus pi. Using basic simplification, we can express 1 minus pi as shown here. Understandably, probability of not owning a car is also a function of z, which is in turn a function of income. These expressions of pi and 1 minus pi will be useful to us later when we simplify the likelihood function of the Logit model. To obtain the likelihood function for the Logit model, we need to understand the distribution of the dependent variable x. As we know, x can take only two values in our sample, it can either be 1 or 0. This type of variables are known as the Bernoulli random variables that can only take two possible values. We can say that x follows a Bernoulli distribution, which is a special case of the binomial distribution. The general form of the probability mass function of a Bernoulli random variable is shown here. In our example, k will be our variable x, which can either be 1 or 0. We can then write the probability mass function as shown here. Another way to express this function is like an equation with p raised to the power x multiplied by 1 minus p raised to the power 1 minus x, where x is either 1 or 0. Both these expressions have the same meaning, they are just expressed differently for convenience. We can obtain the likelihood function from this probability mass function. However, we need to make certain assumptions about the sample to get there. Suppose we have a sample of n observations. Each observation is a Bernoulli random variable because it can either be 1 or 0. We have already expressed the probability mass function of Bernoulli random variables. However, we need to obtain the joint probability of all the n observations. To obtain the joint probability of all the n sample values of x, we have to assume that the observations are identically and independently distributed. This means that all have the same or identical distribution and all the observations are mutually independent and do not affect each other. Under this IID assumption, we can express the joint probability by taking the product of the individual functions as shown here. This joint probability function is known as the likelihood function. Instead of the likelihood function, it is easier to work with log likelihood. So, we take the natural log of this likelihood function to arrive at the expression shown here. We can simplify it further while working with sigmoid function in the Logit model. Remember that we derived the pi and 1 minus pi earlier. We can substitute those values in the expression here and get the value of ln pi upon 1 minus pi. By substituting these values in the log likelihood, we can arrive at the function shown here. We can say that this is the log likelihood function for the Logit model example of car ownership. In maximum likelihood estimation, our objective is to maximize this log likelihood function. This implies that we have to obtain the values of parameters in such a way that the probability of observing the sample values of x is at the maximum. To do this, we use partial differentiation with respect to the parameters beta1 and beta2 and set the expressions to 0. We can then apply the second-order condition to check whether the parameter values maximize the log likelihood function. We cannot explicitly solve these resulting equations, and we have to use iterative procedures. In these iterative procedures, we start from some initial values of parameters and try to adjust those values step by step to arrive at the parameter values that maximize the log likelihood. Some of the most common iterative procedures include Newton-Raphson method and the Broyden-Fletcher-Goldfarb-Shano or BFGS method. the interpretation of the coefficients from the Logit model does not make much economic sense. This is because it shows changes in log odds with a change in the independent variable. In our example, with a 1-unit increase in income, the log odds of car ownership will increase by beta 2. Earlier, we derived the expression shown here when we were discussing the log likelihood function. Here, pi represents the probability of car ownership and 1 minus pi is the probability of not owning a car. Pi divided by 1 minus pi are known as the odds, and taking the natural logarithm gives us the log odds. From this expression, we can see that with a 1-unit increase in income, the log odds will increase by beta 2. However, this doesn't really tell us anything. As a result, we often estimate the marginal effects after Logit model. The marginal effects will show the change in the probability of dependent variable x due to a change in the independent variable income. In OLS, the coefficients themselves are the marginal effects. But this is not the case in the Logit model as we have seen. To calculate the marginal effects, we need to take the partial derivative of the probability of car ownership or pi with respect to income or y. Since pi is a function of zi and zi is a function of yi, we can use the chain rule to express this as shown here. Here, the partial derivative of zi with respect to yi is straightforward and it is equal to the coefficient beta 2. Therefore, we can easily adjust the formula by substituting beta 2 into it. Now, we have to take the partial derivative of pi with respect to zi as shown here. After simplifying, we arrive at the expression e raised to the power minus ci divided by the square of 1 plus e raised to the power minus ci. Hence, we have derived the formula of marginal effects as shown here. We can also substitute zi with our estimated coefficients and equation beta 1 cap plus beta 2 cap multiplied by y. When we carefully look at this formula, we can understand the nature of the Logit model and its marginal effects better. Earlier in our tutorials, we mentioned that the changes in probability have to be different at different levels of independent variables. We used the example of income to illustrate why the probability of owning a car should change slowly at extreme levels of income. Therefore, the change in probability due to income will be different at different levels. That is, change in probability is a function of the income level. We can see this in the formula of marginal effects because the independent variable of income or y appears in the formula itself. Hence, the marginal effects and change in probability will be different at different levels of income. This is true in general for the Logit model, where the marginal effects are different at different levels of independent variables. Due to this, it becomes important to consider the values of independent variables when estimating the marginal effects. We have to ask ourselves a very specific question. At what level of independent variables do we want to estimate the marginal effects? For our car ownership example, we might be interested in analyzing the changes from mean income. Then the marginal effects will show the changes in probability of owning a car as income increases by a small amount from its mean. Similarly, we can choose any level of income that we are interested in. If we choose 1,000 for example, the marginal effects will show the change in probability of owning a car as income increases by a small amount from 1,000. If we have multiple independent variables in the model, we have to choose the values of all the independent variables where we want to estimate the marginal effects. Thank you for watching and I will see you in the next tutorial.